All right, let's go ahead and get started. So we have Zuguang Gu from German Cancer Research Center, and he will be talking about our GREAT package. GREAT is a great tool that everyone should know. And Zuguang, stage is yours. Please go ahead.
Okay, thanks. Hello, everyone. My name is Zuguang Gu, and I'm from German Cancer Research Center, Heidelberg, Germany. And today I will make a package demonstration package called rGREAT, which performs functional enrichment on genomic regions. So talking about the functional enrichment analysis, and I think this is like a basic analysis in bioinformatics. So I think most of you might have already done the so-called overrepresentation analysis, which applies on genes and mostly gene ontology gene sets to find the significant enriched geotarms. So let's say the traditional ORA analysis basically tries to solve this problem. So we have a list of potentially expressed genes and genes in the gene set, and we want to evaluate whether the new genes are significantly enriched in the genes in the gene set. And normally it is done by Fisher's exact test or by hypergeometric distribution. So now when we do genomic data analysis, our data basically most of time are genomic regions. So we have a list of regions, and we are also interested in what are the significant biological functions these regions are associated to. I think many people will do like they will first annotate the regions to genes according to the nearest genes TSS, and then it's like conversion from regions to genes. And when they have the list of genes, then they can apply the traditional ORA analysis. So if we think this question in more detail, actually, when we have a list of regions, and if we do for example, the enrichment analysis, our null hypothesis is, the genomic regions are randomly distributed in the genome. While for the ORA analysis, the null assumption is the genes are randomly selected genome, where every gene is selected with equal probability. So for the traditional way of applying functional enrichment on genomic regions, actually, it's like a mapping from regions to genes, and then to apply the ORA analysis. And there is a problem occurs for this conversion from the regions to genes, because if we assume the regions are randomly distributed in the genome with equal probability, after this conversion, the genes are not randomly selected with equal probability, mainly because some genes are very long, some genes are very short. So the regions are more likely to be associated to longer genes. And for the regions, they can be like in clusters in the genome. So if there's a cluster close to a gene, then the regions in this cluster are more likely to be associated to a genes. So in this case, in this region to gene conversion, the genes are not selected with equal probability, which means the ORA-based methods might not be proper. So to solve this problem, there's a new method. Maybe many of you have already known this method. It's called GREAT. So in the ORA analysis, the genes are the basic unit, and then we test genes against the gene set. For the GREAT method, the basic unit for the analysis are the genomic regions. So basically, they apply and they evaluate the regions to a set of so-called the region set. So a region set is a list of regions in the genome which are associated to a specific biological function. So this GREAT method can be illustrated by this diagram. So on the top, which is let's say the old ORA based method. So we have a list of input regions, and we first annotate two genes based on this nearest TSS rule. And when we have a list of genes, then with a collection of gene sets, we apply the traditional or the standard array analysis, and we have the enrichment result. And for the GREAT method, so it directly applies the method to the regions to generate the enrichment table, but converting gene sets to region sets. In this process, every gene is extended at its TSS, and the gene sets are converted to a region set. And this slide illustrates how this region sets are constructed. So basically, for the GREAT method, it supports three different methods, where the first one is base plus extension. I think it's the most used one. So I will just explain the first method for extending TSS to construct this region set. So there are three genes in the genome, and these are the TSS. And first, for each gene, a basal domain is constructed by extending, for example, 5 kb upstream, 2 kb downstream. So every gene has a basal region associated, and then an extended region is extending the basal region upstream, downstream, maximum, let's say, 1000 kb, or until it reaches the basal domain of the next gene. So for example, this gene to the right, it just extends to the this is the downstream until it reaches the neighbor gene's basal domain. So in this case, every gene has a domain associated, and let's say there's a gene set contains these first two genes, and the region set are the union of the extended domain of these two genes. So in this case, from this position to this position, so these regions are associated with this gene set with two genes, or we can say this is a functional domain associated to the function of this two gene set. And for the second method, basically it's a simplification of the first one, where there is no basal domain. And last one basically is the nearest gene method, where every gene extends until the middle of the two neighbor genes. So it's like the nearest gene rule. So once we have, for a specific biological function, there is a set of functional domain associated with it. And if we have a list of input regions, then the GREAT applies the binomial method to calculate the p-values. So let's say this is a genome, and these are the genes, the black and the green genes. And the green ones corresponds to a gene set, genes in a gene set. And the green lines, black lines corresponds to the domain associated to every gene, and the red lines corresponds to the functional domain specifically for this gene set, the green gene set. And to calculate a p-value, so we first only keep these the green lines, which are the functional domain. Let's say the function, let's call it the cell cycle function. So these are the regions in the genome that are associated with the cell cycle function, and the proportion of these red lines in the genome is 0.6. So we'll say if there's a region randomly selected from the genome, then there is a probability of 0.6 that this region is associated with cell cycle. Then we have a list of input regions, and we just and the number of the input regions falling in the cell cycle associate functional domains. These numbers follows a binomial distribution, and then we can calculate the p-value. So this is the model of the GREAT method, and it also supports the background. So for the GREAT, the background is more like a universe set. So it's like a universe set where the input region is randomly sampled from the universe set. So again, so this is the genome, and this is the, say, cell cycle associated functional domains in the genome, and the blue triangles are the input regions, and the red ones are the background background regions. So we can imagine, let's say these blue regions, for example, they are differentially methylated regions for in a specific tissue, and the red one, these red regions are the possible differentially methylated regions in all tissues. So the red regions are like a universe set, and in this case we can the number of blue regions falling in this red region can be modeled as following a hypergeometric distribution, and we can calculate a p-value from it. So GREAT is represented as a web-based tool, and this is a web-based its interface, and I can show you. It can be accessed from this link. And the package I will introduce today is called rGREAT package, and it has two main functionalities. The first is it can because the original GREAT is a web-based tool, and the user needs to manually upload regions and to click and to check the result from the website. And this there's the one functionality from the rGREAT package. It can automatically submit the regions to the GREAT web server, and to automatically retrieve the result from the web server. So you don't need to directly interact with the GREAT web server, and you can do it programmatically. And the second functionality is, as I have already explained, the binomial method or the hypergeometric method is actually it's quite easy, and the rGREAT package also implements this algorithm, and so I call it the local GREAT analysis, which it can apply GREAT analysis completely locally, and also it can use this annotation resource from the Bioconductor and to support more organisms and to support more types of gene sets. So I will first demonstrate the use of online GREAT analysis, and there is a Markdown rendered HTML document which you can access in this link or this link. So these two basically are the same. So if you want to try the code, you can type. So this is my name, zuguang.de without s, so http zuguang.de or https joker.goo.github.io. So I'll just give you 5 seconds to type this URL. 5, 4, 3, 2, 1. Okay. And go to talks, and here, item 7, and we will first go through this one. So this is a rendered HTML document, and I also have the source code of this Markdown document, and I will just run these commands one by one. So I first load the package. And the input for the analysis is the regions. So it can be a data frame. So for example, this contains the peak regions of a transcription factor, JUN. So it's basically a data frame. And basically only the first 3 columns will be used. So if you cannot access this file, you can also generate a random set of regions. So for example, in this case, the bed object is a gREAT object. So it doesn't matter whether it's a data frame or a gREAT object, because internally they will be converted to the data frame. So I will still use first an example. And with this data frame, we can run this function, submit GREAT job. So it will automatically submit these regions to the GREAT web server. And in the meantime, I will also do the online analysis by providing this specifier, and I will just submit. And here you can see for the GREAT web server, it only supports four different genomes, two organisms, four genomes. Just submit. Oh. Just refresh it. Okay, it's strange. I will just skip using this web service. I will just focus on the this R Markdown document. So when you have successfully submitted the job, and if you type this object, it will give you some basic information of the version of the GREAT, the genome, how many regions, and some this is the parameters for extending the TSS. And the next step. So now we have submit the regions to the GREAT web server, and then the next step is to retrieve the enrichment tables. So GREAT provides several gene set databases, and they can be accessed by this function, available ontologies. So for current version of GREAT, it provides seven categories of gene sets. So 3 GO gene sets and the other 4. And by default, the 3 GO gene set will be downloaded. Then we can use this function, get enrichment tables. It will just download the enrichment table for the first 3 GO gene sets. Then when you type the job object again, you will see actually it says the 3 enrichment tables have been downloaded. This TBL object is basically a list of data frames, because for each gene set category, and it is a table, a data frame. So the TBL basically is a list of data frame. So by default, there are 3 data frames. We can see. So this is the first data frame, GO molecular function. And the second one, GO biological process, and the last one, GO cellular component. So these are the enrichment tables. And if you only want the enrichment table for the GO biological process, then you can just say TB equals to TBL and the name of it. This gives you the enrichment table only for the GO biological process analysis. So this is a simple data frame. And in the data frame, there are several columns. So the ID, the GO ID, the GO name, and the columns start with binom. They are the analysis from the binomial method, and where this column is the number of regions in the gene in the functional domain of this gene set. And this is like a full change of the observation divided by the expected number of regions, and the p-value. The p-value from the binomial distribution and the adjusted p-value. And there are also columns start with hyper. So these are the traditional gene-based ORA analysis. I would suggest not to look at these columns, because, as I said, the motivation of the GREAT method is to let's say correct the wrong hypothesis if you directly use the ORA method. So I would suggest only to look at the columns start with binom. Okay, and then there are some functions, visualization functions. So for example, this one, it plots the volcano plot. So if you do differential expression analysis, and normally you will make a volcano plot, which like a symmetric volcano. And for the enrichment analysis, normally we'll only look at the overrepresentation. So the volcano is basically like half volcano. And the x-axis corresponds to the log 2-fold enrichment, and the y-axis as a minus log 10 p-value or just p-values. And the size corresponds to the number of regions in every functional domains. So we can see actually these points are composed by a list of curves, and actually each curve corresponds to a specific number of regions in the functional domains. And we can also see, and if the gene set is larger, it's easier to be significant. So larger the point, it means larger the gene set. And there are some other plots which are the same as from the GREAT website. So if you have done some analysis directly on GREAT website, then you'll be familiar with this kind of plot. So there are 3 plots. The first one, so this is like a global distribution of the regions of the analysis. So this is a number of associated genes per region. So this means there are 387 regions which only associated with one gene, and there are like 1,300 regions associated with 2 genes. The second plot and the third plot are the distance to the gene TSS in these different windows. The third one is the absolute distance to the TSS. And you can also make this plot for the regions in a specific for a specific term. And you can get the association between the regions and the genes by get region gene association function. So this returns a gerange object. And this means in this geoterm, in the genomic domains associated with this geoterm, there are 6 input regions falling in, and these are the genes associated to these regions. And these are the distance to the TSS of these genes. And there's also a function called Shiny report, which can generate a simple Shiny app to realize or to summarize the enrichment result. Let me check what I can run this function. So it will take some time because it will first download all the enrichment table from the GREAT web server. I think it will take 10 seconds, I guess. And in the meantime, I can introduce the last functionality. So in this example, actually, if you check the number of significant geoterms, you will find there are around 800 geoterms that are very significant. In this case, it's very difficult to summarize what are the general functions from these 800 geoterms. So you can use this package, which also developed by me, called Simplify Enrichment. And there's a function called Simplify Geo, which you just provide a list of significant geoterms, and it will generate a plot, a summarized plot, like this one, just to summarize the general biological function in the enrichment result. So there are 800 geoterms in this analysis, and this heat map is the similarity of geoterms, and it has been clustered. And on the right side are the word clouds visualization showing the where there are keywords, basically showing the general functions of the enrichment result. And let's check this Shiny app, which is here. So basically, this is the information from the object, and can see this global plot and this enrichment tables. And so there are all these different gene sets categories are also listed in this Shine app: geomolecular function, geobiological process, blah blah blah. And for each category, there is a table which contains all these columns, and it's a volcano plot, and you can pick whether you use log-to-fold change or z-score, or whether you use the p-value or the adjusted p-value for making the volcano plot. And you can also click on each term, and it goes to where? I think it should. Okay, I think there might be a problem. So for each one, if you click on the term, it will lead you to the web page on the GREAT server of this term. Okay, now we continue to introduce the local GREAT analysis. Okay, so basically the local GREAT implements the GREAT algorithm locally, but it has a different background model compared to the online GREAT analysis. So if we go back to the online, the background model for the online version, basically this background is more like a universe set. And for the local one, this background is like a mask from the genome. So A, B, C, D basically is the same as the original GREAT algorithm. So these are the functional domains, and the red triangles are the input regions. And we can use a binomial distribution to calculate the p-value. And for the local GREAT, and it supports to define a mask background in the genome. For example, the red one, these red regions are the background regions or the background mask regions. And once it is provided, then all the analyses are restricted only within these red boxes, and also with a binomial distribution method. And the original universe set can also is basically a special case of this mask background method. So let's say this is the original background method in GREAT, where this red are the background. And if we just think this red background, they are masks. In this case, the genome will be segmented also into these very discrete regions. And in this case, we can also model it as a binomial distribution. And in general, the hypergeometric distribution can be approximated to a binomial distribution. And for the local GREAT analysis, basically it gives very identical, very similar result as the online GREAT analysis. The advantage is the local GREAT analysis supports a lot of built-in gene set. It also supports self-defined gene set. It supports many organisms, genomes, not only these model organisms, but also hundreds more organisms. And it uses the annotation resource from Bioconductor, so it can ensure the annotation resource is always up to date. Okay, now I will just demonstrate the local GREAT analysis. So if you go to my my personal website, it's this one, demo one, local GREAT and HTML. Okay, so first load the package, and for the local GREAT analysis, the input must be a the G-ranges object. So I first read the region as a data frame, then I just convert it to a G-range object. So the GR is the input for the local GREAT analysis. And the function called GREAT is the core function to perform this local analysis. And it accepts it has three arguments. The first one is the input region. The second corresponds to the gene sets, and the third corresponds to the genome. So for the local GREAT, it by default supports many, let's say, built-in gene sets, gene ontology, and many, let's say, standard organisms on Bioconductor. So taking human as an example, we can simply specify I will use GOBP gene sets, and the organism, the genome of the input region is an HG19 genome version. And we can run this line. And for the GO gene set, it will take about 20 seconds, because I think there are around 20,000 gene sets in GOBP ontology. Yeah, there are 15,000. So it will take 10 seconds to 15 seconds, I guess. Okay, so if you print the return object, it will give you some basic information. You can see it uses standard TXTP package from Bioconductor, and it uses the standard organism annotation package from Bioconductor. Okay, so the result is the results are stored in this object. So before introducing how to get this table from this object, I will just introduce what gene sets and what organisms are supported in local GREAT. So if we run this line, it returns a table. So these are the organisms or genome supported in local GREAT analysis. You can see there are quite a lot. So there are like 40 rows of this data frame. So basically, mouse, human mouse, and this rat, blah 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 blah. I think I should directly print the data frame in the terminal. Here. So all these species are supported in the local analysis, where you can simply specify the name of the genome, which is in this column here. Basically, just specify this column, and you specify GOBP or GOMF or GOCC, then it will automatically apply the local GREAT analysis. And for the local analysis, it also supports, by default, supports M6DB gene set, but only for human. Basically, you also specify a predefined text here. For example, if you want to perform analysis on the hallmark gene sets from the M6DB database, you just specify M6DB-H, and it performs the enrichment on the hallmark gene sets. And of course, it supports all these different categories of the M6DB gene sets. You basically specify these names of these gene sets. So for example, you can also you can just remove this M6DB prefix. You can just say H. H means a hallmark gene set. And for example, C2CP, which is identical to this one. Okay, so by default, local GREAT supports gene ontology gene sets and the M6DB gene sets. So there are, of course, many other gene sets available. And this, so the local GREAT analysis also supports to provide self-defined gene sets. So in this example, I will just demonstrate. So here I have a list of gene sets from this so-called D6DB. I think it's called drug signature database. It also provides gene sets. So the GS is a gene set. The format is a list of gene vectors. So this is a gene set which contains a list of genes in entrance gene ID, and this is the second gene set. So this is a gene set, a self-defined gene set. And basically it just simply provides the list of gene vectors as the second argument of the GREAT function, and it will apply the analysis, you can see. And in this case, the gene set becomes self-provided. And the next example is to use the KGG gene set. So to obtain the KGG gene set, we can use the rGREAT package to directly download the gene sets from the KGG database and perform some simple filtering, reformatting things, and we will have a KGG gene set. So this is one KGG pathway, and these other genes in the first pathway, and these other genes in the second pathway. And similarly, we just provide the KGG gene sets to the function. It will apply the analysis. It's fast because the KGG gene sets are small. The last scenario is mainly for non-model organisms where you should self-define both gene sets and the TSS. So in this case, the first is the input region, the second is a list of genes, and the third one you need to provide the location or the coordinate of genes for this non-model organism. To input the gene set, which is a list of gene vectors, and you need to provide the TSS or the gene definition. Then the local GREAT will automatically extend the TSS to construct the functional domains for every gene set. I don't have such non-model organism. I will just take the human HG19 genome as an example. So I first construct coordinate of genes. So the genes, for this one, it only contains the coordinates and there's no other information. So just assume this is from an unknown genome or a genome less well studied. So it only has the chromosome names and the coordinates. And because we have already had this gene set from upstream analysis, previous analysis, now we have a list of genes and we have the gene definition in the genome. It's okay to run this GREAT function. So basically it's successfully run, but there is a warning message here. It tells you, because for the gene definition, there's no information of the length of the chromosome. So by default, it will take the length of the chromosome will be calculated based on the first gene and the last gene on the genome. I mean, in most scenarios, it's okay. But still, if it's not provided, it will give you such warning. And to get rid of this warning, we can manually add the chromosome length to the gene object. So basically assign a named vector of the chromosome length, and we use seek length function. And in this case, there's no such warning. And the next, we can set a background for the analysis, like a mask background for the analysis. So in most cases, the gap regions in the genome are removed, are excluded from the analysis. So in this case, we can specify the exclude argument to the regions that you want to exclude from the analysis. So this function is like a helper function, which automatically downloads the gap regions from UCSC table browser, and it returns a GREAT object. And if we provide this object to exclude arguments, then these regions will be removed from an analysis. So all the GREAT analysis will be restricted in non-gap regions. And for example, if you can have such background regions from upstream analysis, for example, your background region is a set of regions which have the same, let's say, CBG density as your input regions. So this region can also be set as a background regions. Then we can specify it with the background argument. So exclude just to exclude these regions, and background means only include these regions in analysis. If the regions you want to exclude or include are basically chromosomes, then you can also specify a list of chromosome names. So this one means only to perform the analysis in the autosomes. And we can also use exclude equals to chromosome X and chromosome Y. So these two commands are identical. Okay, now next I will introduce how to get the enrichment table from the object returned by the GREAT function. So basically we use this function, get enrichment table function, and it returns a table. So it's a data frame similar as the one from the online GREAT analysis. So geo ID, the name of the geo term, and some statistics. And these two columns are the p-values and adjust p-values from the binomial method. And from these columns are the result from the ORA-based method. So the reason why I keep these regions basically to make them consistent as the online GREAT analysis, but I recommend only to look at these the columns related to the binomial method. There is a new columns in the local GREAT enrichment table, which is mean TSS distance. So this is the mean distance from the regions to the TSS. And so basically p-values measures the statistical meaningfulness of the analysis. And you can also think this column, mean TSS distance, is kind of like biologically meaningfulness of the analysis. So if you think your regions are promoter related regions, then you might set a cutoff of this column. I need to take those regions which are close to TSS. And similarly, you can also make a volcano plot, half volcano plot. Basically, it's basically same as in the online GREAT analysis. X-axis as a log fold enrichment. The y-axis is minus log 10 p-value or adjust p-values. And this plot means the name of the function are the same. So make this global distribution plot, and to get the association between input regions and the genes. And you can also make such plot only for one specific term, geo term, for example, and the associations for the regions that only overlap to the function domains related to this geo term. And there's also a Shiny app. Okay, let me try this time. On the local GREAT analysis. So it looks very similar. It gives you many tables, a volcano plot. In this case, I think you can click on a specific term and there will be a window pop up. So this is a plot specifically for this gene set, and these are the associations between regions and the genes. Okay, so next topic is how to work with other organisms. So by default, local GREAT support is standard organism packages on Bioconductor, and it's very easy to extend the analysis to many other organisms. So method one use the biomat genes in the gene set. So I have another package called biomat gene set, which has already compared gene coordinates and the gene set for more than 600 organisms. And basically, you just specify this argument biomat database to it's called ensemble dataset, which is the name of the organisms on the ensemble database. And the name can be obtained by this command. So you first need to install this package biomat geogeneset. and you just run this command. There will be a HTML page, and you can just search your organism here. So basically, you use the first column as a value for the function, and just search. So here you can search your organism, and you need to be careful is this column, the version. So you need to be careful that the version of the genome is consistent as your input regions. Okay, so in this example, I just performed the GREAT analysis on Panda. So this function is like a help function just to generate a random set of regions for a specific ensemble genome. So with the input regions, the geo gene set, and the biomat data set, then you can perform GREAT analysis on a non-model organism. And the second, use the M6DB gene sets. So officially, M6DB only supports human, and recently it also supports mouse. There is a package called M6DBR, which provides gene set of many other organisms. So in total, 20 organisms, just by mapping the genes to the orthologs in other species. So you can see actually it supports many other organisms. So you can use this gene set for some other organisms. So for example, if I want to perform enrichment analysis on the hallmark gene set on chimpanzee genome, so basically you can specify the species equals to chimpanzee, and the hallmark gene set, it returns a table. So it's a table, basically a table. And to use this gene set for the GREAT analysis, we need to convert it to a list of gene vectors. And then we take this column, gene GS name, which is like a gene set ID and the intrinsic gene. And you can basically take these two columns out and apply this split function. We can get a list of genes. Let's see, list of genes. And for the chimpanzee genome, there is already a standard TXTP package on Bioconductor. So in this case, we only need to specify the version of the genome of chimpanzee, and then we can apply the enrichment analysis on the chimpanzee genome. See. Okay, the last method is to use NCBI genomes. The reason is actually, if you know this annotation hub package, actually you will find there are many it's called orgDB object available for a huge number of other organisms. So on the Bioconductor as a package, there are this org HSEGDB package for, let's say, around 20 standard organisms. But on annotation hub package, there you can find, I think, more than, I don't know, 500 more such organism annotation objects from there. In this case, we can use this external information for many other organisms for the enrichment analysis. So taking dolphin as example, so this is its Latin name, and we first need to download the organism annotation object, the orgDB object from annotation hub package. So I first load this one. Okay, and actually it's not very straightforward to find the correct data set from annotation hub. So basically I would use the display function. There will be a shiny app which contains a table. Where you can search a specific data set. It is more suggested to use to search by a species Latin name. So I will just search this one. In this column, and I will also filter this column to orgDB. So you can see we have found this orgDB object for the dolphin, and we take this ID AH108.106. And here we just provide this ID as the index of the AH object. Then we can obtain the organism object. Oh, sorry. So this is the rGDB object for dolphin, and we can use this object to extract the geo gene sets. So it's actually these two steps are quite are not straightforward. I mean, if you know these two functions, it's very easy to understand. So this line to extract all GOBP terms. That's 3,370. So this can be read as extracting all the geo terms where the ontology equals to BP. So all the GOBP terms, and then we can take the genes and associate to every of these GOBP terms. Okay, now this BO gene sets is the list of gene vectors, and then we can use it for the analysis. So now we have the gene set, but we do not have the coordinate of genes. So unfortunately, on the annotation help package, there's no such information. But luckily, such information is available on the NCBI database. So in the rGREAT package, I have written a function called get genome data from NCBI, which can automatically download the genome information and the gene information for a given genome in a given organism. So again, let's take dolphin as example. To run this function, we need to know the refseq accession number for the organism. So this is not very straightforward. So you need to go to the NCBI genome website, and you need to search dolphin. And normally, it's better to use the Latin name to search. The Latin name is this one. Oh, yeah. And the first one is the current version, and you need to use this ID. The refseq assembly ID. I think this is also okay, but it's more suggested to use this ID. And you provide this ID to this function, get the genome data from NCBI.
Zuguang, we are over time, so maybe you can go.
Yeah, there's only 10 lines left. So you provide this refseq accession ID, and it returns the coordinate of genes. And with genes and also with gene set, we can apply the GREAT analysis, and it gives you the result. So that's basically the use of local GREAT analysis for both, let's say, standard organisms and also for self-defined organisms. So that's basically everything for this package demonstration. So in the future, if you have questions on this package, you can simply write me an email or ask questions on GitHub. Thank you.
All right, thank you. So we don't have much time, so we close here, and please reach out to Zuguang if you have questions.